Okay, so this video is getting us back to where we started our calculus discussion, and that was that calculus was really invented to study velocity. And so we want to think about average velocity again, as we talked about last time. Average velocity is defined by the change in displacement over the change in time. Now I'm using the word displacement instead of distance, right? Because distance is always positive, while displacement could be positive or negative. So what I mean by that is, like if you were -3 units away, that might mean that the negative might refer to being on the left, and then positive being on the right. Or positive may mean up and negative means down, and so on. And so displacement can be positive or negative. Positive or negative. Distance would only be positive. And that's also the difference between speed and velocity, right? Speed is the absolute value of velocity. So continuing, if s of t is displacement at time t, and time runs from t equal a to t equal b, then the average velocity would be equal to s of b minus s of a divided by b minus a. Good. Now instead of using a b, suppose I want to really focus in on the change from the point A. So if I start at the point A and I go out to B, what I'm going to be doing is I'm changing my notation slightly so that we can bring a value of x into the point A. So instead of using point B, I'm going to use a plus h, and so the distance out here is h. And so I'm going to say that instead of b, I'm going to write a plus h. Okay, I hope that doesn't confuse you. We started with a and b to begin with, but we want to change notation slightly. Okay, so that gives me a plus h minus a in the denominator. And so notice that the denominator does simplify to just h. Okay, and so then graphically, right, this would be your s of a, this would be your s of a plus h. And so what you're looking at here is the slope of the line between those 2 points, right? So the slope is s of a plus h. Well, it's the change of s over change in s over change in time, right? Good, which is what we have with the star. Good. All right. So then that's the average velocity, and of course we already gave away the punchline in section 2.1. We talk about the instantaneous velocity. Is going to be the limit as h goes to 0 of s of a plus h minus s of a divided by h. And we're going to call that the velocity at time a, so this is velocity. Okay, so let's actually compute this for a specific position function. Whoops, I don't know where that came from. Let s of t be equal to t squared. Okay, and then let a equal 1. And then we'll take the limit as h goes to 0 of s of 1 plus h minus s of 1 divided by h. And so let's plug those numbers in to t squared. So that's going to be 1 plus h squared. Does that look like a 4 or an h? 1 plus h squared minus 1 squared divided by h. Good. And now we're back to our normal limit routine, right, from the earlier sections. So now we want to simplify that. 1 plus, remember to FOIL this out, right? So that'd be 1 plus 2h plus h squared minus 1 divided by h. Now, the 1's cancel. You can factor an h out. So let's write that in the next line. H factors out. 2 plus h. Notice I'm being pretty careful here about my canceling. The h's now cancel, and at this point we're able to substitute h equals 0 in, and we get 2. Good. So what we've just shown is that the velocity at time 1, is equal to 2. Good. This also means that the slope of the tangent line, at t equals 1 is 2. So geometrically, what have we just found? Sorry about the squeaky chair. I need to get that fixed one of these days. There's my t squared. Here's my a equals 1. And so here's the slope, here's the line. And what we just determined is that the slope is 2. And so therefore we can even write the equation of the tangent line, because we have the slope and the point for the line, right? And so therefore the equation of the line is just going to be using the point slope form. I guess we were using t, huh? Good. All right. So we know the velocity is the slope of the tangent line. Good. So let's wrap this up here and take a look at a couple of definitions. Definition 1. The line tangent to f of x at x equals a, and then is the line through the point a f of a with slope given by the limit as h goes to 0 of f of a plus h minus f of a divided by h. Good. Definition 2. This is the big definition, the derivative of f at let's say x equals a is denoted by f prime of a, and be right that f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h, provided the limit exists. Very good. Now, did everybody catch how I said this in English? Right? This is, let me put a little dot there. The dot here is that this is read as f prime at a, right? F prime at a. Very good. So we already know how to compute the derivative. We've been computing them actually in some of the previous sections, but now we're going to do more. Okay, so we're just about at the 10-minute mark, so I think I'm going to wait, and then in the next video we're just going to work through a few examples.